Have you ever imagined what it feels like to undergo a surgery while still being conscious? Well, people have really undergone that. Prior to the discovery of anesthesia in 1846, all surgeries from minor to major were performed on people who were wide awake and held down on the operating table by men whose only job was to ignore the patient's screams and sobs. But anesthetics have been saving us from the traumatic experiences. The first ever anesthetic to come into action was ether. Its ability to induce loss of consciousness was first demonstrated on a tumor patient at a Massachusetts hospital in 1846 within a surgical theater that later became known as the ether dome. Despite health professionals using it every day for more than 150 years, the molecular mechanism by which anesthetics produce their effects was unclear. In a recent study, scientists from Scripps Research in San Diego described the mechanism behind general anesthesia in unprecedented detail. The proposed mechanism is based on the disruption of lipid rafts, which is the plasma membrane of cells containing combinations of cholesterol and protein receptors. This triggers the ion channels and ultimately stops neurons from firing. A postdoctoral researcher in the Hansen lab bathed cells in the chloroform and watched something like the opening shot of games of billiards. Temporary exposure to anesthesia causes the lipid clusters to move from an ordered state to a disordered one and then back again, leading to a multitude of subsequent effects that ultimately causes changes in consciousness. What he was looking at was a shift in the GM1 clusters from a tightly packed ball to a disrupted mess. As it grew disordered, GM1 spilled its contents, which was an enzyme called PLD2. Tagging PLD2 with the fluorescent chemical, Hansen was able to watch as PLD2 moved like a billiard ball away from its GM1 home and over to a lipid clusters called PIP2. This activated key molecules within PIP2 clusters called TREC1. The TREC1 potassium channels release potassium, and that hyperpolarizes the nerve and makes it more difficult to fire and just shuts it down. The activation of TREC1 basically freezes neurons' ability to fire and thus leads to a loss of consciousness. As a traditional method, researchers wanted to validate the findings in a living animal model. The common fruit fly Drosophila melanogaster provided that data. In fact, they required double the exposure to the anesthetic to demonstrate the same response. Now that we know the work of anesthetics, this discovery raised a host of tantalizing new possibilities that may explain other mysteries of the brain, including what leads us to fall asleep. Thank you for watching. Subscribe to our channel for more videos like this.